Okay, welcome back. Anyway, this is Digital Systems Implementation. I've called it Chapter 5 Star. It's an expansion upon what we talked about on Chapter 5. Really, we're still talking about delay, signal propagation, and here we'll actually get into some transmission line effects. This is a reference book where I think some of this material came from. This is a book that I don't have and I never read it, so more accurately, these notes are probably derived from that book, but I've modified them a little bit, and I'm not sure who derived them in the first place. Anyway, we're still talking about signal propagation and T-line effects. The classical approach to determine switching speeds of a digital block is typically based on the assumption that the loads are mainly capacitive and lumped, and that's often and usually the case. When we do have to worry about propagation of a signal along a line, you can model it as a lumped or distributed resistance and capacitance and inductance, and its characteristics would depend also upon the source, the line itself, and the terminating impedance. For long lines, a distributed RC may dominate, in which case you can't really treat it like a lumped circuit, and that's particularly the case if the line spans the chip or a significant portion of it. And it also arises as designers certainly want to have more and more speed and performance out of their devices. So here's the lumped model. You sort of think of a driver as an inverter, let's say, for example, and it's driving a long capacitive line, and these are essentially the parasitic capacitance associated with that line. And what we would just end up calculating sort of the lumped value, which is the length of the line times the capacitance per unit length of that line, in which case we'd end up with a circuit that looks like this. This associates the resistance with the resistance of the driver, and then the capacitance of that line, and it's no longer distributed, but we just think of it as all those small capacitors added together. And that's perhaps the easiest to see and probably the most familiar kind of RC kind of time constant associated with signal rise and fall time. It's a relatively simple model, allows us to estimate delay for logic gates with purely capacitive loads. And once the load is determined, the dynamic behavior of the circuit, sort of its switching times and whatnot, can be quite easily estimated. The conventional delay estimation approach seeks to classify three main components, and these are purely capacitive. That's an internal capacitance associated with the transistors. That's not so easy to see or to calculate by hand, but basically we'd be given some values based on the size of the transistors. The interconnect themselves, it's a little bit easier to see because these things look like parallel plate capacitors, and perhaps a little less easy to see the input capacitance of the gates that we're fanning out to, but still relatively easy to see. These load conditions imposed by the interconnect lines could present serious problems, particularly once you get up into gigahertz kind of frequencies, in which case it'll look a little bit more like a distributed RC kind of wouldn't call it propagation, but diffusion along a line. Anyway, here's our simple lumped model. The simple inverter here is driving three other inverters, and the lines of interconnect are of different length and geometry. So we sort of assume that the load of each interconnect line will contribute to the load seen by this inverter here. So it's just all of these capacitances here added together. So the total load seen by the driver is simply the sum of all those capacitive components. And then the switching characteristics of the inverter is going to be governed by the charge and discharge time of the load capacitor. And typically you need some type of computational geometry, basically back annotating from the layout to give you more accurate values of what those capacitors happen to be. So this is a simple RC circuit, as we've already seen many times, and we're interested in, let's say, the fall time and the rise time. And we're looking at fan-out limitations. So basically what we see here is an inverter driving similar gates. There's three of them here, and these all contribute, looking out this way, can contribute to the capacitive load seen by this inverter. So it's interconnect as well as these gate capacitances, and it also looks back into the output of this inverter itself, and it would contribute to the capacitance. And since these all are in parallel, they'll tend to add. Now when we're driving, let's say, H NAND gates, and we're interested in the rise time, so basically we're trying to pull this node up here to VDD, and we're interested often in a worst case, so it's going to be one of these transistors that's functioning. at a gate level, this is kind of what we're looking at. One 2-input NAND gate driving a whole bunch of similar 2-input NAND gates, so there's H copies of them. So the total pull-up time would be something on the order of 6 plus 4H times RC. And this is sort of from our calculations that we looked at before when we were looking at that Elmore delay. So the R comes from one PMOS pull-up device. That's worst case. So one of these will pull it up. It's of width 2. So remember that the mobility of holes is less than an electron. So it effectively has a resistance of 1 R. The 6C is from the driving gate output. So this is calculated from the diffusion seen on this NMOS transistor and these two diffusions seen on these two PMOS transistors. So per unit length they're contributing C, so there's 6 of those, so that's the 6C that's sitting there. The 4HC is from the H gates being driven, so we're looking down here, we're driving 4 H similar gates, and the 4C itself comes from looking into this gate here. So it's as if we had an output coming here going to H copies of this, and if we look at this we see we have a gate width of 2 here and a gate width of 2 here, so that's where the 4C came from. Similar calculation then for NAND gate driving H NAND gates, and we're interested in the fall time. It would be very similar type of calculation. It'd look a little bit different because now we're pulling this node here down through these two transistors. So now we're really more interested in that Elmore type delay, and the circuit's going to look something like this, and we can identify the components. And once we've got this circuit, it's easy enough for us to calculate the pull down time, or an approximate pull down time. We're going to see it's equal to 7 plus 4 HRC, and so to see how that comes about. This is the capacitance seen on this output node, and then the 4 gates that we're talking to, which are H of them, and each of 4 contribute 4C. This will be pulled down through a resistor, which has a resistance of R by 2. Remember, it's 2 wide, but it's an NMOS transistor, so it's R by 2. And then this node here is also pulled down through this transistor down here, which contributes an R by 2 over here. This transistor here pulls down this node here, which was a 2C. It's 2C or 4C. You can argue either way around, but it's going to be something. And certainly this pointing out where those values are. So when you want to estimate the circuit total delay, this isn't very accurate, but it gives you an idea sort of what's happening. We're going to want to look at similar scenarios, but for each of those gates and what they're driving. So the first thing we have to know are things like the W over L ratios. In this case, they're set up so that the effective R's are that of a unit inverter with R in the pull up and R in the pull down. And there's an assignment there sort of set to, if you were driving this 3-input NAND gate, what would be reasonable values of P and N? And you should be able to calculate those. And so this is a scenario we're going to be interested in. The input changing here, the output's changing here. This is set up so that the toggles the transition through that NAND gate, toggles the transition through the inverter, set up so you toggle the transition through the NOR gate, and then you've got an output load that you're charging up, and it's a value 12C. So the way to do this is you do them in sections. So in this case here, we're interested in this node being pulled down. So it's an inverter here. It's an N-type device. It's of width 1, so it contributes R to the pull down. And we got to calculate what the output capacitance is seen by this guy here. Well, it's got a PMOS transistor which is width 2 and an NMOS transistor width 1, so it's a 3C contribution here. And then it has devices here that it's talking to, which are going to be 2 in the pull up, 2 in the pull down, so that's 4 for that device, 4 for this device, 4 for this device, 4 for this device. So altogether that's 19C. Similarly, you do something in the middle here and you make that calculation, and that shouldn't be too difficult to do. Sort of leave it as an in-class assignment. Similarly, for this stage you do the same thing, and then for the output stage you do the same thing. So if you pay attention to a fair bit of detail there, you'll see that you'll end up with a D, which is on the order of 64 RC, and that's just a rough calculation. Of course, you could use a much better circuit simulator like SPICE or something, but this sort of lets you know what the delays are and what the contributing factors are, and sort of the big picture. Point out that these are still back of the envelope type calculations. Certainly wouldn't replace a more detailed simulator and something that back annotates data. But it does provide an idea of the types of calculations used to estimate worst case delays. And like I pointed out before, clearly for a large circuit one would employ more sophisticated CAD tools than the back of the envelope calculations. Okay, but one of the things you might note here is that with respect to synthesis, the logic doesn't tend to get too deep because the delay would get too long. And so here's in-class assignment, I guess transmission line 0. Do the same for the opposite transitions on the previous circuit example. And we'll take a brief break at this time.